Okay. Yes, so I will present this topic today. And yeah, so here is my content for today, and I would like to start with the general story. So yeah, so we have highly relied on fossil fuel for energy supply, energy source supply so far, and then this is a big problem because fossil fuel emits a lot of huge amount of greenhouse gas, and then which significantly contributes to climate change. And actually, many countries are aiming to reach carbon neutrality by 2050. And then, yes, we need definitely the eco-friendly new energy source. And then, and hydrogen is really good because hydrogen is one of fossil fuel alternatives. And this is really good because it is safely transported in pipeline, or its combustion is in water. And also the most important point is zero greenhouse gas emission. And then how? Okay.
Just okay.
Oh yeah.
Are you pressing the arrow? Yeah. Arrow, right and left.
Ah, okay. Thank you. Then how can we make, or how can we obtain this green energy source, hydrogen? So this is a representative process of hydrogen energy production, which is called electrochemical water splitting. Also, the overall water splitting reaction is the sum of hydrogen evolution reaction, HER, and oxygen evolution reaction, OER, which occurs at the cathode and anode respectively. And so significant efforts have been devoted to the designing new catalyst for this water splitting. And especially for regarding OER process, the transfer of multiple protons and electrons are involved in OER process. So it is highly thermodynamically and kinetically demanding. So we need new ideas. So one of the ideas is the designing of multi-Schottky electrocatalyst by forming nitrogen-doped graphene shell on the surface of catalyst nanoparticles. And then, so what is multi-Schottky heterojunction electrocatalyst? So in general, metal and semiconductor are connected to each other. Charge transfer occurs because of difference of parallel two materials, and until parallel and two materials are aligned at the equilibrium state. And then after that, this energy barrier are formed, and it is really helpful for charge separation. And so it can promote electron transfer from semiconductor to metal, which is really helpful, charge separation. So we took this advantage of multi-Schottky heterojunction electrocatalyst to produce our catalyst system. And then our theoretical work is motivated by 2 points. So one of them, the first of all, is like the effect of different phases of metal for like catalyst, because metal can have different phases. For example, HCP or FCC, like those kind of phases, and then they can have also different effects on catalytic reactivity. But this effect, like the effect of different phases of metal on the like not only OER but also like other catalytic catalyst performance, was rarely studied. So we just wanted to know about that. And secondly, there are 3 key factors to determine the catalytic reactivity, which are, for example, electrical conductivity and surface reaction kinetics and ion transfer efficiency. So those key factors, 3 key factors, have been really well analyzed by experimental analysis. For example, like Nyquist plot or linear sweep automatic matrix or something. But the problem is, by depth calculations, okay, electrical conductivity and surface reaction kinetics have been well analyzed by, for example, like density of states or like Gibbs free energy landscape. But what about ion transfer efficiency? Unfortunately, it has been not well explained or not considered well so far. So to understand the catalytic reactivity, or like to understand ion transfer efficiency, the effect of ion transfer efficiency or relationship between ion transfer efficiency and catalyst performance, we designed this supercell structure for depth calculations based on this experimental results, HRTM image of cobalt nitrogen doped carbon NC nanoparticles. So this graphene, nitrogen doped graphene has both pyrolytic and pyridinic base. And then I will show you our results. So this is the experimental result. So as you can see, our catalyst has showed low overpotential or low charge transfer resistance, which is related to high electrical conductivity, and also they have a rich active surface area. So I would say our catalyst showed outstanding catalyst performance of water oxidation. And then our theoretical work performs to try to explain the reason why our catalyst system shows outstanding catalyst performance. So so we consider the first key factor, electrical conductivity. So to compare electrical conductivity, we compared this like electron population at 0 electron volts. This is a Fermi level, so we should compare like electron population at a Fermi level. And as you can see, they're really similar, like regardless of phase of cobalt or like types of graphene. So I would say there is no significant difference of electron population at Fermi level, like both of them. So we cannot explain well, we cannot explain well the synergistic effect of like coexistence of cobalt like HCP and FCC phases. And then also, then we considered surface reaction kinetics. And This graph seems complicated, but I just will just explain this blue line and pink line. So this FCC phases like cobalt FCC with just graphene, and this pink line is FCC phase of cobalt with pyridinic. They show the high energy barrier, which means really not good for OER catalytic activity. So I would say FCC phase of cobalt cannot contribute to our like outstanding performance. And then just accept this blue line and pink line. We can see this rest of them more deeply. So we calculated like at two different pH values. So when pH value decreases from 14 to 12, what is it? The sky blue color. It shows energy barrier now. So we can say, okay, when pH value decrease, and then catalytic activity can be lower. But also this page cannot also explain well the synergistic effect of coexistence, like two phases of cobalt in our catalyst system. Then we missed the one key factor, ion diffusion efficiency. So we assumed that, okay, maybe this ion diffusion efficiency can help us to explain the reason why our catalyst system can have really high efficiency. So before we consider this key factor or ion diffusion efficiency, we have to think about the problem during a problem which occurs during OER process. So because OER process has like multiple transfer of like 4 electrons and 4 protons transfer. So then this hydrogen ions can be accumulated on the catalyst surface, and then this accumulated hydrogen ions on the surface can degrade catalytic activity. So it leads to local pH reduction, I would say. So so we need additional repulsive force towards hydrogen ions to like prevent the local pH reduction on the surface near the surface by like getting rid of hydrogen ions on the surface. And then okay, normally in general we only consider the ion diffusion, which is relatively weak driving force for ion mobility. Animation doesn't work, but yeah, we only considered ion diffusion this part. But in heterojunction structure, they can the built-in electric field at the interface can be formed, like between semiconductor and metal. And then, for example, the case one, like if a built-in electric field points to the left, and then hydrogen ions can be attracted by built-in electric field. And then case two, the built-in electric field is positive x direction. Then it can behave as repulsive force. So it's like equation. So this term is for ion diffusion part, and this one new term is for considering the additional driving force by built-in electric field. So yeah, so we will use this equation to consider ion diffusion efficiency. Then this is our theoretical result. So this ATCP part, they showed a nearly zero electric field value. On the contrary, this FCC part, they have built-in electric field near the catalytic surface. Then these effects can behave the strong driving force to transport hydrogen ion on the surface. So in our case, built-in electric field points to the right. So like these hydrogen ions can be repulsed from the surface, catalytic surface. So built-in electric field in our catalytic system can prevent local page reduction, leading to enhancement of like OER catalytic reactivity. Yes, so now we can finally explain the synergistic effect of coexistence of HCP and FCC in our catalytic system. So HCP, this part, like OER can mainly dominantly occur on this part, but the problem is local phase reduction can degrade catalytic reactivity. But luckily, FCC part can help this HCP part. So built-in electric field was formed. This FCC part at the interface. Then this built-in electric field can help this degradation of catalytic activity by strong additional driving force from built-in electric field. So yeah, so we can consider three key factors by TF calculations. So I just would like to thank my provider, Professor Mato and Dr. Choi, and yeah, my group members, and thank you for your kind attention.
Question, very nice work. So you talked about FCP and HCP, I believe, Cobalt. That's metallic.
Our catalysis system.
Yes, is it metallic fully or? You just need
You want to
Yeah.
measure it?
It's okay. Metallic, okay. So these
You can send me the pen drive.
conditions, electrochemical are quite harsh. So how can you keep one system from flopping into the other? Or how you could propose to make either system in the, I mean, experimental? I'm just curious.
With the XRD characterization.
Yes, but I mean, yeah, but how I make, okay, I said, okay, today I want HCP, tomorrow I want FCP, so how is it possible to make, I'm not familiar with the system, that's why I'm asking. It's maybe a stupid question, but I just don't know the system.
Did you consider only the cobalt in both phases and see if a certain phase transition can occur in the condition?
Only in the conference. Only in the initial synthesis step. I don't think.
I know, but you have to check if first if the problem or the phenomenon occurs already in the metal, and then see what happens when you consider interfaces. So my answer was, did you also study the problem only for the metal in the two ACP and CCP, the two polymorphs, let's say? maybe you can check the translation between the two phases, and if you have the graph or stability of phases. This was my question. If there's some study of you or other groups.
In this work, the interface was stabilized even during the reactions. And one phase is one sample is only made of FCC, and one is only with Atcp, and the other mixed phase. But the mixed phase was the best one because the FCC makes the good surface direction kinetics, and Atcp opposite. Atcp makes the good surface direction kinetics, but FCC makes strong electric field to push the proton away. Okay, so that the pH, local pH value is kept high for active emission. So they have different phases, have different roles.
Are you attending this
One is
meeting
for surface,
on your device?
That's the reason I'm studying a similar problem in a solid electrolyte. And maybe, I guess that at the electrode interface, generally a change in phase or also in amorphization may occur.
Your PPT is not
Not still, we don't know exactly still, but
it's
moving in that
nothing
direction.
inside.
I think that you need to investigate the phases
Yeah,
of the
just
cobalt
checking it out.
itself, and then, let's say, make the problem more complex, go to the interface. That's what we are.
That's why I'm
focused on.
saying that
I know that's the problem.
As we said, diversity matters, right? We are big sure. That sounds realistic. Yeah, thank you.
can you give me your email ID? Yeah, I can share you.
Okay,
It's
it's
very
MJ.
interesting, so.
Sorry.
I tried
Yeah.
to. The one I registered for, right?
Yeah, yeah. Any email ID.
Okay.
Yes, yes. Okay.
There you go.
Yeah, I've sent it to you. Did you got?
No.
No. Where is the it's do you have the
Yes, I got it now.
yeah, just click it on the link.
Guys, why we start right, I mean, to apologize to everybody because force the family to read to a meeting that it's not very simple that I have to take my mouse and click to know that it's me, so it will be on Zoom like this. I cannot move that meeting. So don't hate me for that. Just
Yeah, you can be ready.
Okay. Are you gonna use the microphone?
Yes. Emails.
No, you need another piece to connect.
How will I connect this?
Yeah, there is no HDMI here. So can you just open the presentation? I can send it to you by email. Can I use the same email?
But, this device is for him, and he want that device, and that's why I'm asking. Okay.
Okay, just give me your email address. I'll try to send you the PowerPoint.
Yeah, the same email ID.
Send me your ID. Okay, I reply. Reply.